Great. So this is the second day into um, admin of code warmup. So I suppose we can get right into it. So the first thing that I wanted to do is look at a few utility functions that I've added. And I'm going to be looking for opportunities to sort of beef this up um, so that we can be more speedy when the 2020 competition arrives. It's coming up fast. It's on Monday. So any preparation that we can do before then is going to be good. So I have my pget function here, which we've gone over in a previous stream, but um, this downloads my uh, problem input for a given year, and the admin of code creators will be pleased to note that if I do a check to see if the file was already downloaded, and if it does, then we don't actually do an HTTP request. We just read it from disk. So they post about that on Reddit. They want to minimize traffic to the server, which I totally understand. But yeah, this is like, we can do pget. If we looked at like 2019, 12, something like this. I went over this in one of my previous videos. It's like a three-body problem type of deal. But yeah, and then we have a few parsing functions here. So I use this a ton, this sort of train, membership, partition and close, and then attack left or right. And this will just read, this will read respectively integers and parse them into integers. Signed integers, which is just, we also add hyphen to the list of characters that we care about. And then we can get out characters, and this handles either uppercase or lowercase characters. So there are a lot of problems where you're getting like identifiers out or stuff like that. So if I look at, these functions aren't really anything special, but like, so if this is my problem input, then I can do, for each p, give me signed integers, like so. And so I can use that to parse out problem inputs, or if there was something like, so in 2019, there was this problem 14, where we had these identifiers for different like chemicals and reactions and stuff, and I can get just the characters out of those. And then I started thinking about graph problems and just sort of grid problems in general. And so I think we're going to go over one of those before we get back into the 2017 problems. So I have what I'm calling DIRs here, and this is just, so these are just the increments. These are kind of the cardinal direction increments on a XY coordinate plane. So we have +1 on the x-axis, -1 on the x-axis, +1 on the y-axis, -1 on the y-axis. And then the code for this is just, we're making an identity matrix of size 2. This is a pretty standard APL idiom. And then we're just using a train to say, take that and then put it on top of the negation of itself. And that gives us our directions. And this is useful. These directions are going to be useful in a lot of problems where we're dealing with grids. I think like 2019 day 3, we were doing this like wire counting intersection type of thing. And they're also useful for graph problems, which I want to take a look at. So actually, to explain the make graph function, let's go ahead and take a look at a problem from 2016. Day 24, which I solved, today off stream in the course of making this function, but I think it's useful to go over it anyway. So in admin of codes, there are several problems where you get these type of mazes, which is basically, you get this text file, and then these pound signs represent like walls or impassable terrain or whatever. And then the other characters are usually either dots for like empty space, but they can have various other interesting things inside. So for this problem, we have numeric identifiers. So let's take a look at this. I may have already actually put this into a, Yes, I did. Okay, great. So then I can just parse this. Uh, yep, okay, great. So what I usually want to do with these problems, um, a lot of them just boil down to um, like graph problems, so like finding shortest path, um, mm, like spanning trees, that sort of thing. And Dialog has a number of functions in the sort of standard library. I'm not sure if it's really a standard library or not, but it ships with Dialog. It's called defins or defined functions. And in there are several functions which operate on graphs. So you can see here, this is the graph section. So we have like breadth first spanning trees. We have shortest path to from strongly connected components. We even have stuff like uh, News Algorithm X implementing exact for exact cover problems, this sort of thing. And for most of these functions, they want the graph in a particular format, which is a vector of cells, and then each cell is itself a vector of integers that the integers represent indices where there's a connection between that node and a different node. Um, so maybe there's an explanation here. Yeah, so the graphs will look kind of like this. I think there's one here with a diagram that maybe makes this. Might just be in the graphs section. Right, yeah, so we have this graph like this, where A is connected to C and B, and then C is connected to D, etc. And there's 8, so there's 5 vertices, then there's 8 edges. And so for each one of these vertices, they're going to have cells that represent indices where you can um, that represent a connection from one to the other, like this, right? So A has a connection to nodes at indices 2 and 3. This is all one. I think this is in index origin 1, so just keep that in mind. And then the node at 2 has a connection to 3, and then 2, 4, etc. And so, like, if you look at these first two, pretend that this is like node A, it has a connection to B and C, and then B has a connection to C. And if we look at the diagram, we can see that that's the case. So A to B to C, and then B to C. And if you want, so these graphs are directed by default, but if you want bidirectionality, then you just include indices in both of the source and destination cells. So all that being said, I have a makeGraph function that will take a character matrix like this, a maze, and will generate a graph out of all of the traversable spaces, right? So it'll basically take out the walls, and then it builds a graph in this format that we can then feed to the defins functions, and we can do things like shortest path or strongly connecting components or whatever. So how does makeGraph actually work? So first off, yeah, if I just look at P, and we can kind of look at this in sections. So the first thing that I do is I say, okay, tell me where the pound sign is not equal. That gives us an array of ones here, and then we can use the where operator to tell us the indices where that's true. So these are now all of the indices in our drawing where there's traversable space. And then, so before I go any farther, I should just initialize G, and we just assign it to the empty list. It doesn't really matter because we're going to fill it up later. And then once we have all of these indices, now we can say, all right, for each one of these cells, I want to take the 4 cardinal directions, our DIRS matrix that I showed you previously, and I want to add that to whatever the current coordinate is, And if the resulting coordinate is in our list of locations of traversable space, then I want you to add a link there, right? So for each one of these coordinates, we're expanding out in the 4 cardinal directions. We're checking to see if that's a valid space to move, basically. And if it is, then we're going to find the index of that new space, and we're going to place that index into the resulting cell in the graph. So for this one, this will be so for each NS, these locations that we found, we're going to take dirs plus rank 1 W. And yeah, this just, right now, this just gives us a matrix of sort of the coordinates of the four directions where you can go from each space. Of course, we have to filter out the ones that don't work. So we can filter out, and then we want to say, oh, actually, sorry. Yeah, right away we can just say ns index of split. And so we can find the index of all of these elements in our locations or our elements of traversable space. Index of has this interesting property where if you don't, if the element is not found in the left argument, then it will return a number greater than the length of that argument. But it depends on index origins. So now we basically just want to filter out numbers. You see all these like 21s here? I want to get rid of those. So that's going to be without, no, 1 plus, right. So yeah, and that gives us, so each one of these vectors now represents the indices of the of a connecting node. And you can sort of see that this makes sense. So because we're going in sort of Ravel order, basically left to right, top down. So the first cell where there's traversable space is this 0 here. And you can see that it has links to 10 and 2. So 2 is going to be the cell that's directly to the right of it. And then 10 must be this one that's down here. And then we have a bunch of cells that are basically linked to the one in front of it and the one preceding. So we have like 3, 1, 4, 2, 5, 3, et cetera, et cetera. And then once we get over here, now this is the corner, so this is 2. And you can see that it links to cell 11 and cell 8, which is the one preceding. And then we just, because we have this graph, now we can just assign it to G, right? And yeah, let's make graphs. So, and then the only other thing to say about it is that I have this thing with IO over here, because depending on the problem, I'm either going to be in like index origin 0 or index origin 1. And so this is kind of a agnostic way to do that, which basically says like, hey, if we're in index origin 1, then just add 1 to the length and filter that out, because that's going to be the invalid result that the index of function returns. So yeah, we have P, and if I just say like make graph P, it doesn't do anything, but if I type G, then this is our resulting graph. So I think that this is a very useful function. I know that there were a ton of these maze problems in 2019, and I'm betting that there's going to be more, but we can go through this this 2016 day 24 just to show kind of how this works. So the problem itself is basically, I think this is essentially like traveling salesman or something. Like we start at location 0, and we want to know the shortest path that the shortest path that will visit all of the other numbers in in our maze. And so, I mean, I don't think that there's like an efficient way to do this that's not just brute force, because I'm pretty sure that this is like NP hard or NP complete. So that probably means that our problem is going to be small enough to brute force. So let's just, we can just do that. Um, so what we're going to want to do is, so we have quad D, which gives us all the digit characters, and we can say for each one, um, W equals P. And this is just going to tell us, where these digits are um, in our input maze, and then we can just say where. And so you can see from this output that it looks like only numbers 0, 1, 2, 3, and 4 are present in the maze, which looks like it is. So we can concatenate these together and then disclose to get this. And these are basically the locations of our numbers in the maze, right? And well, actually, if if we do the same thing for p that we did inside of our makeGraph function, so does not equal p index of. Now these are the indices in our graph which correspond to. So we have g, and so you can see that the first element in our graph corresponds to the 0 character. And then the third element in our graph is 4, 2 corresponds to 1, et cetera, et cetera. So now, because we have everything set up to do this, we can look at the path function in the defins library. And so path gives us, as it says, the shortest path between two indices in a particular graph. So, by the way, so I've mentioned this before, but the goal this year is speed. So I'm going to use every tool available to me, and if that includes, predefined functions in the defins library to look up shortest paths and all that sort of thing, then I'm going to use them. Although depending on how much time we have available, I might try and do it manually just to show you how you would solve a problem like this in APL. The fun thing about defins is that, of course, all the source code is available, and generally this is like very well explained, flows nicely. This is really good code in general. So you can kind of look into this library to see how you would solve certain problems if you're not aware of how to do it. But anyway, for our current purposes, we will import the path library. And now, if we take G, we can do like, hey, what's the fastest path from like 1 to 20? And this path, the path function actually gives you the indices of all of the nodes that are visited along the shortest path. So if you want to know the number of steps, then you can take the length, right? But you have to subtract 1 because the list of nodes visited includes both the start and the destination. And if you're just looking at steps, like let's say that you wanted to know how long the path was from one cell to a cell that's directly adjacent to it, well, that length would be 2 because it's going to be the start cell and the destination cell. But you only stepped 1, right? So the actual distance you traveled is only 1 unit. So you subtract 1 here when you're looking at lengths. And what we're actually going to do for this problem is we're just going to take all of our numbers and we're going to find the shortest path between all of them. So we're going to have, so this is numblocks. We're going to use an outer product here. And this is G path, comma. So this is a train. It's going to take the left index and the right index, concatenate them together, and then feed it into path, like so. And this gives us this gives us the indices that are visited along the path, as I was saying. So we can just do this. We can do like a length to top, like that. That gives us the links, and then we just have to do a neg1 plus. So we have zeros along the diagonal, which makes sense because there's, it's a zero distance trip to visit yourself, I guess. But now we have this matrix where you can to find the length of the shortest path between any two numbers. We just have to find the index of it. So like for this one, what's the shortest path between nodes 1 and 2? It's 2. How about 3 and 5? It's 10. So this question says, given your actual map and starting from location 0, what is the fewest number of steps required to visit every non-zero number marked on the map at least once? So for this one, we're going to be using another defense function. Told you I'm going to make use of this year. Called PMAP, which gives us a permutation matrix of a particular size. So you can do like, if you do PMAP3, this is all the permutations of the range from 1 to 3, and same for 4 or whatever. And so if we do this, if we do a permutation of the number of numbers that we're looking at, we get this. It's a fairly long list, as you might imagine. But actually, the problem with this list is that our starting location needs to be fixed at 1, and this includes 1 through 5 for the starting locations. So what we really want is neg1 here, pmat 1 cons. And so this is all the permutations of, hang on. Yeah, there we go. So this is all the permutations of all of the other numbers starting from 1, right? And now we can do a windowed catenate like this. This gives us all the coordinates of the trips that we need to take. And we can say, oh, did I, give me 1 second. Did I actually assign this? I did not. So this is going to be our paths. And then for each one of these, we can just say index into paths, like so. And this tells us how long each trip takes. In order to figure out how long it takes for the entire row, we just sum it. And then we want the minimum. And we get 14. Which for the test input is correct. So all that's left is to actually do this for our problem inputs. pget 2016-24. I'm pretty sure I want to mix this. Geez. Gotta get faster on the keyboard shortcuts. Yep. So now we can say, all right, make graph P. We have our graph, which is fairly substantial, 4174. And if I come back here, I want to find this. Number locations. Sure, so these are the locations of our numbers. Interestingly enough, you can see that we only have 8. So again, this isn't going to be anything crazy because we have to, as far as I know, we're essentially required to brute force this. So yeah, this is going to be Index error. Oh, sure, because I didn't assign paths. This is actually fairly fast, right? I don't know. This takes under a second. Anyway, I haven't timed it exactly. And then we can do this. We get that, and again, we're just gonna sum and find the minimum. We get 490, which is the answer. So by having functions to set up these graphs for us, we can save a little bit of time, and then we can more easily make use of the built-in functions that we have available. Part 2 is pretty easy with this setup, by the way. So now it's just what is the fewest number of steps required to start at 0, visit every non-zero number marked on the map, and then return to 0. And so in order to do this, we just need to add a 1 on the end of all of our rows. And we get 744. So yeah, I think this is a useful function. I'm going to keep this in my toolbox, but I wanted to walk through it and show why I think it's useful. All right. So with that out of the way, and I'll probably, like I said, I'm going to be on the lookout for other utility functions and things that I can add. And you know what? If you have ideas, things you want to, things that work for you, or that you want to suggest, I am all ears. So yeah, just contact me. Okay, day 10. By the way, I'm not sure. I don't know how long the stream is going to be today. I was shooting for like maybe an hour. I did 2 hours last night, and that was pretty lengthy. So I think I'm going to keep it to like an hour tonight. Okay. These explanations. Current position, skip size, sequence of links, your puzzle input. Okay, so this is 2016 problem 10. Nope, it is 2017 problem 10. Right. Ooh, I get to use my int function. So take int. Beautiful. Okay. Reverse the order of that length of elements in the list. Move the current position forward by that length plus skip size, and increase the skip size by 1. And the list is circular. Okay, so we're going to be doing... We had a problem yesterday where we ended up doing like modular indices. So I think we're going to be doing that again. So I want to be an IO 0 here. I have chat open on my phone. Yeah, I didn't think anyone was here. Yeah, so I'm going to be an IO 0, and the list begins at 0, 1, 2, 3, 4. Current position. Current position, skip size. Okay, so we'll do CP, SS. They're both 0. Right, and then give an input links of 3, 4, 1, 5. So we're going to write a function that's like iota 5, and then 3, 4, 1, 5. And this is going to be a recursive function in all likelihood. So we'll say alpha match Zilda, return W, otherwise. The list begins. Right. First link 3, select. Okay, so this will be take alpha iota current position plus, right, 0, 1, 2. And yeah, again, because it's circular, we need to do like length W mod. And then we'll say at W, you want to reverse 21034. Yep, that's correct. Okay, and then we want to recurse with that along with one drop alpha. Oh, but we have to do some, what happens with the skip size? Where are we using that? Move the current position forward by that length plus the skip size. Okay, oh man. Okay, so this is going to be new W. CP is going to increment by the first take alpha skip size plus, right? Skip size is going to increment by 1. I guess we can get this stuff out of here. Oh yeah. And then we can recurse with the new W and 1 drop alpha. Let's just run it. Let's see what happens. 34210. Oh, interesting. Oh, that worked. How about that? So, yeah, so CPSS 00, and then the question is 2 take multiply reduce, right? We get 12. Yep. Okay, so we have some links, and we're just basically going to run this on P, and it wants us to do this 256. So rather than iota 5, it'll be iota 256. 23,715, which is the answer. All right, this at syntax with the reverse is really nice for these type of problems. Oh geez, I remember this one. This one's annoying. All right. The logic you've constructed forms a single round of the not hash algorithm. Running the full thing requires many of these rounds. Convert characters to bytes using your ASCII code, so we'll be using quad UCS. And just to make sure that that's the case, 49, 44, 50, yeah. Okay, great. Add the following links to the $17.31. Okay, fine. uh, uh, length pad, I guess. Instead of merely running one round like you did above, run a total of 64 rounds, using the same length sequence in each round. The current position and skip size should be preserved between rounds. Okay. It's fine, actually. Yeah. Called the dense hash. To do this, use numeric bitwise. Dude, some of these problems are ridiculously overspecified. So we're at a total of 64 rounds. Okay, well, this is going to be P cons L pad, right? And now can I just like run this 64 times? Power operator and recursion. I don't know if I've ever done that before. Uh, Interesting. Huh. Okay. Start with the previous round's current position and skip size. Yep, because I'm not resetting those in between running, so I think it's fine. Called the sparse hash. Your next task is to reduce those to a list of only 16 numbers called the dense hash. Okay. So we're going to do 16, 16 row, apparently. And then for some of these, oh geez. All right. Well, so now I have to binary decode, apparently. I always get these mixed up. Binary encode. And this is going to be 8 row 0. They're all 8-bit numbers. Row 2, W. Right? And then or reduce. I get this. If I do this rank 0, they'll already be in a matrix, right? Yeah. Oh, but these answers are quite different. Sixteen, 16, 8. Uh, okay. In the interest of speed, I'm just gonna go back to what I had. Easier. To a list of only 16 numbers called the dense hash. As a single hexadecimal string. Okay, then we need to yes, yes, and then for each 16, 16 in encode W in list. This will be quad D and then lowercase quad A enclose index A9F 9F. That is not the correct answer. Current position and skip size should be preserved between rounds. Use numeric bitwise exclusive OR. The tricky thing about this is that it is, hey kitty, meow. The tricky thing about this is that it's difficult, like they don't offer you any test cases for this part. And there is a ton of code here, any part of which could be broken in some way. I'm pretty confident in this function here because it gave us part 1. What if I jot like this? That doesn't change anything. Okay. E9F. Oh, of course, because, hang on. pget 2017 is 2017, right? 10. UCS LPAD, right? This is what it actually wanted. So if I put that in here instead, then I get 541 DC. Oh, that's actually the right answer. 541 DC 31, etc. Okay, I was just operating on the wrong input. When you have a long problem description like that, it's easy to get lost, I guess. But wow, look at this function. This thing's a behemoth. Look at this. Gross. And I wish that there was an easier way to do these binary conversions, but I'm not too worried about it, I guess. there's this variant of dialog called dialog extended that has some additional operators for dealing with binary conversions that are a little bit nicer than what you get in standard dialog. But I'm not going to use it for. It's like it's not really officially supported and et cetera, et cetera. So, all right. I mean, this is fine, I guess. So I think I'm going to change up these warm-up streams. So previously I'd been like putting together some code and then trying to like, format things nicely um, and I think it's probably more interesting if I just like speed through problems so that you guys have um, Born Swift. You're missing a that actually that so this emoji you're giving me legitimately looks like APL code, I have to say. That's funny. What's up, Cody? How's it going? Um, yeah, so I think I'm just actually just gonna speed through some problems, and it's probably more interesting. Um, and don't worry, I'll still like format the answers and post them on GitHub. Although I know I haven't done that yet, but I will do it soon. So you can go through and look up at the cleaned up answers and look at the transformations that happen between when I'm like live solving the problem versus when I'm trying to format it for publication. Anyway, okay, so problem 11. Uh, it's gotten lost in an infinite grid. It's a hex grid. Gross. Very gross. Pget 2017-11. Yeah, and it's just the one line, right? Ooh, I can use chars. Check it out. Yeah, that'll be P. Um, I, you know, I've dealt with this a few times. I don't really know any like good data structures for doing hex grids. The only thing that I really know how to do with this is just like work with XY coordinates. And there might be like a better data structure or some other way to store this so that it's more easily traversable, but whatever. We're gonna do some math. So, all right. So if I have a hex grid, um, assume that I start in the middle at origin 0, 0, right? And basically this means that I have uh, I have 6 points spaced evenly around me at distance 1, right? So if I go 1 to this is saying, if I go 1 to the north, then I'm at the center of a new hex. If I go 1 to the northeast, I'm at the center of a new hex, etc., etc. And so we can use some trigonometry to get the xy coordinates of the centers of those resulting hexagons. And so we can start by saying, so how will this work? So dialog APL's trigonometric functions are denoted in radians. So 2 pi is a full circle. So I want, I do like iota 6 divided by 2. Ooh, right? This is, no, that's not what I want. Divided by 3? Yeah, that's right. Okay, so in range 2, these are sort of the 6 points that are equidistantly, or equally spaced. I can do pi times, right? These are the angles in radians. But actually, hang on. So if I want my hexagon spaced kind of north-south, then I think I need to add 0.5 here, yeah. Pi times. And then I don't do much trigonometry, but let's see. Um, so sine, cosine. What if I just do this? Mismatched. Right. So this will be rank 1, 0. Ooh, interesting. Oh man. Oh, this floating point stuff is going to be ugly. So these e to the negative 17s are essentially 0. But because of floating points. Well, anyway, so we can read this as like, okay, so due north is one element up and 0 to the left or right. Um, and then what is this, northwest? Is this really right? 105? These never really change. Let me think about that. That might be accurate actually. Yeah, I think it is. Okay, great. So, and then to the northwest, we go 0.5 up and then negative 0.8, I guess this is. Um, 0.5 down, whatever. Okay, so let's call these steps. And then, what are my directions going to be? Uh, so now we have north, northwest, southwest, south, right? Southeast, northeast. And then because we have single characters in there, we want to make sure that they're all lists. And we'll call these hexters. Uh, those are all lists, right? Hexters for each shape. Yeah, okay, great. And now, so we have P hexters, index of P, gives me all these. I can enclose this and then index it into steps, right? And if I add all the way down, this gives me the coordinates of where we end up after following our problem input. And the question says, you have the path the child process took. Starting where he started, you need to determine the fewest number of steps required to reach him. So we can't really do much with the coordinates here because it's not like straight line distance. So like we can't just do Manhattan distance or whatever. I don't have a great way to solve this. But I think we can basically do like a greedy algorithm where we just take a step. So we'll call this like destination. Where we like take a step in the direction that minimizes the distance to our destination. And then we increment a counter. So we'll keep a counter, C0. And then we're going to operate on dest. We have some steps. And I want to know, give me like dest minus rank 1 steps. W. Oh. right? So one of these is going to be the minimum in terms of distance. And how do I find the distance? Distance will be well, I guess it's Pythagorean theorem, right? So uh, it's square each one, add them together, take the square root. And then tell me what the index of the minimum is. Zero, apparently, which is accurate. And then use that to index into steps. We get this. Dest plus, and then we're going to want to recurse on that. Sorry, dest minus. So in this instance, we've moved due south. Yeah, this is probably fine. I'm willing to try it anyway. So we have some recursion stuff to deal with. I don't think any of these distances are going to be greater than so I have to deal with the floating point thing. So if 0.1 is greater than W, this should be W as well. And dot, then return C. Otherwise increment C. Let's see if we get an infinite loop. We did not. 722. Oh, which is the correct answer. Okay, so yeah, we're doing like a greedy algorithm here. What's up, cat? And we're just taking the step that moves us the closest direction to our destination. And then once the destination is small enough, it's never going to be zero because of floating point inaccuracies, then we just return the count. Okay, great. How many steps away is the furthest he ever got from his starting position? Good question. Get out of here. So again, I don't know a great way to do this, but I can assign this to a function. And then what was p? So if I do Hexter's index of p. My cat's bothering me now. And then I index this into steps. Instead of adding them, I can do a sum scan first, like this. And then for each one of these, so rank 1, I can run F, and then I can take the maximum. And this is a little bit gross because it's ultra brute force. I actually don't know how many steps there are, but it returned quickly for part 1, so I feel reasonable about it. That is certainly not not the answer. So let's see what happened here. Um, Geez. So my cat recently learned how to play fetch with hair ties. So she'll always like bring us hair ties and then meow until we throw them. And the trick is you got to throw them somewhere where they're not easily reachable, and then she leaves you alone for a while. She's a cute cat though. I do need a rubber band gun. That would be amazing. My cat would love that. Um, what's going on here? Hexter is index of P. Um, Steps index of uh yeah, it has to be enclosed. I mean, this all seems correct. Is the floating point thing getting out of hand? Is it hmm. So if I add all this and then I run F on it, I do still get the right answer, right? No, I don't. Okay, so something changed between. Oh, yes. That's right. It's keeping the count in between. That's just great. All right, so we need to reset the count each time that we call it. So this is now on W, like that. And then if I do this, I thought something was off because that number is like way larger, 1551, which is the correct answer. All right. Um, I'll probably call it here. I've been at this for about an hour and now my cat's bothering me. I can do this one real quick actually. So um, this one is basically strongly connected components. And 2017-12. Yeah, so we get this. And if I just so for each p, give me the integers, and then one drop. This is now, so if we look at p, if we mix it, we can see like the integers on the left represent indices, and the integers on the right represent other indices. And so actually, the nice thing about this is that if we just get rid of the stuff um, before the listing out the destination indices, this is the format that Dialog likes its graphs in, right? So now if we call this G, we can use the strongly connected components function from defins, which implements Tarjan's algorithm, I think. So the question here asks like basically you get a graph specification. It says, hey, the node at index 0 goes to 2, 1 goes to 1, whatever. Um, and yeah, it's like which ones can you reach by doing a depth first, breadth first search, whatever. Um, they are sort of disconnected. So strongly connected components means, 1, 2, and 5. If you're in any of those, you can get to any other one in the group. Um, and similarly, 3, 4, 8, etc. So we can just do SCC on our graph. And how many are in 0? The answer is 152, right? And then here the question is how many, basically it's like how many components are there, or sort of disjoint groups. And the answer for that is we can take unique mask sum 186. So some of these problems, you just the joke in Reddit, I guess, is that you just type import solution in Python and you have everything you need. Strangely enough, sometimes that works for APL as well. So anyway, yeah, that'll do it tonight. Yeah, my friend Cody dropped by, so thanks, Cody. Good to hear from you. Hope you're doing well. You had a happy Thanksgiving and all of that. I'll post the recording for this up on my YouTube channel in case you missed it. It's odd. I mean, I guess I'm speaking to people that are watching it currently, so if they missed it, I guess they'll go to my YouTube anyway. But anyway, I may be on tomorrow to do some more warm up. I might take a break and just sort of conserve my energy for the start of the contest on Monday. But we shall see. In any case, thanks for tuning in.